Okay, welcome back again for the last time. You're almost done. I don't know if you are as tired as the speakers. Probably not, huh? I hope not. So this afternoon I will do a mix of different things. We'll talk about hydrogen. We'll talk about Flammal Interaction, something that has not really been discussed. And I wanted also to spend maybe a few minutes first on detonations. I realized that Moshe touched the topic a little bit, but not much. So I wanted to go back to it also to show you that even for something as apparently complicated as detonation, if you spend maybe 1/2 page of derivations, you can obtain an incredibly precise description of detonations. So I'm just going to do that first, because we did not touch, I think, enough detonations in this course. So if you really want to know, after that, all the details of detonation, the reference in this field is the book by Lee here. And Clavin also just produced a recent book on this topic. Detonation research started a long time ago, actually. It has always been something which was interesting for quite a few people, even so they didn't see that many detonations in those days, but they knew that they should exist somewhere. And so what I want to show you today is that to first order this PV diagram, purely thermodynamic theory, gives you an incredible amount of information on detonations. So before we do the derivation, I just want to show you a detonation, how it looks in a 1D diagram. So this is typically the profile through a 1D detonations. You have here density going up and down, pressure going up and then to a high pressure, mass fractions of reactant going down, and temperature going up. You see those shapes here are not completely random. We will explain them in a minute. The important thing to realize here is that there is a flame structure here, but using theory, you can compute the two states here on the left side and on the far side without having to compute the structure of the flame, which is also what we do for deflagration. Remember, for deflagration, we found that the pressures on both sides were equal, that the temperature on this side was equal to the temperature on that side plus QYF over Cp. But here, not only we will have the state, but we also have the speed of this thing, which is very specific to detonation. We cannot do that for deflagration. A funny thing, by the way, that you can see is that density, pressure, and temperature go up, okay, in a detonation. In a deflagration, temperature goes up, density goes down. The burn gases are light. This is why the flames go up to the sky. In the detonation, it's different. Everything is going up, but interestingly, not in a monotonic way. Pressure is going up, but first it goes up and down, and we will explain that because it's a very important phenomenon for safety, for example. So what do you need? I know that many of you are afraid of touching theory, but again, this is basic theory. There's not much to understand to do that. You just need to write the jump equations between the two sides. Moshe started from the Navier-Stokes equations, but you don't need all of that. You just need to say, I want to know what's conserved between the two sides of a flame. And as you will see in a second, you find two solutions, the deflagration and the detonation. So how do you do it in practice? Now, please bear with me here, because if you don't follow the derivation, it's not so interesting. So one is the fresh gases, two is the burn gases, and we sit on the reference frame of the flame, so obviously the mass must be conserved, nothing new. Rho1 U1 equal Rho2 U2. Momentum tells you also that P1 plus Rho1 U square must be conserved, and then you have the state equation. And then you have the conservation of enthalpy. It's not extremely fancy, okay? It's just, now, just with these equations, and that's what's amazing, just with these equations, we're going to show everything we need on the detonations. So how do you do that? First thing, you don't do it yourself. You talk to one of these old guys, they have been trying to do it for 50 years. They know there are many bad ways and there's one good way. The good way is the following. You start by combining these two equations, okay? To obtain this one, P2 minus P1 equal the difference of the rho u square. And in the rho u square, you introduce m, the flow rate, to obtain this equation. And you do the same thing for the second one here. Here you combine, again, mass flow rate and enthalpy, and you obtain this equation. Now, like always, mathematicians, they don't like to work with your variables because they think it's easier to formulate them with different variables. So pressure, P2 is really what we're looking for. We are wondering, what is the pressure in the burn gases? Well, theoreticians tell you this variable, which is proportional to P2, is a better variable. And for ρ2, this variable is better. Okay? Why? Well, just because when you write the equations, you will see that it's easier to formulate them with these variables compared to P2 and ρ2. So in a detonation, we expect P to be positive, because pressure is going up, and you expect V to be negative because the density ρ2 is more than the density ρ1. Now, the first equation here can be written like this when you go to the new variable. It's just a straight line. P equal minus V multiplied by M1 square. M1 is the Mach number of the detonation or of the deflagration. It's the speed normalized by the sound speed. And you will see that just with these things will show that M1 must be more than a large number, 4, 5, 6, okay, in terms of Mach number. This is why detonations go fast. The second one, you can rewrite it using P and V, and you obtain P plus 1, V plus 1 equal 1. Simple, okay? I mean, it's difficult to do simpler than that. Now, we know that P and V are the two unknowns in our problem, and you have two equations. I guess you can do that if we're 12 years. 12 years old kid can do that, huh? Two equations, two unknowns. Not too difficult. So in practice, the way you do it, you plot a diagram here where you put V in this direction, which is really ρ2, that's what we're looking for, and here you put P, which is really P2. And then you see that you need to find the intersection between this line here, which is the Rayleigh line, and this parabole here, which is P plus 1 equal 1 over V plus 1. Everything I have written here is without combustion for the moment. Okay, you didn't see combustion because it's the non-reacting case. It's what people do around an aircraft when you look for a shock wave. Where is the shock state? It's here. Okay, you start from state 1, you go to this point, and that's the shock conditions. And so if you just want to know here what's the state, you write these two things together, and the solution is P equal M1 square minus 1 and V equal 1 over N1 square minus 1. Which you can come back after that to the P2 and P1. You find the equations that you have learned if you did a course on compressible flows without combustion. You have the pressure jump linked to the upstream Mach number and gamma, the density jump, the temperature jump through a shock. Okay. For the moment, there's no flame. Okay, now you say, okay, I want to do the same thing here again, but now through my interface, I want to have a flame. So let me go back here. So if you do that, you have the same equations. For the first two, you conserve mass the same way. You conserve momentum in the same way. The state equation cannot change. And here, enthalpy has a new term, QR. This is the heat released by the combustion of 1 unit of fresh gases. Okay? That's the one we have defined many times already. And again, you use exactly the same variables. No difficulty here. And you obtain a solution, which I will show you in a minute, where the diagram leads to two solutions. One of them will be a case where pressure is almost constant. Another one will be the one we are interested in, this one, where pressure actually has a big jump through the flame front. That's the detonation. So deflagration, we have talked about them a lot. I don't want to talk about them. I just want to talk about detonation for the moment. So how do you get to find this point up there? Well, you have to solve the equation I've just shown. Now you take this thing, you plug the new P and V variable into it, and you obtain this set of equations. Now, it's exactly the same we had before. P equal minus M1 square, V doesn't change, except now that for the Hugoniot curve, you need to add this Q here, which is the normalized heat release. It's the same thing we had before. So if we look at the solution of this problem, this line doesn't change, but the green line changes a little bit. It goes up by Q, okay? Because when V equals 0, P is equal to Q. So we have just shifted the green line, okay? Again, nothing very complicated. So we see we have two solutions here, one here and one here. By the way, if you look at Q, and you put reasonable numbers for QR, CP, and T1, you find that Q is a big number, at least 10 or something like this. Huh? So we're going to use that later to simplify a little bit the results. So now you see that you have two solutions, which depend on the Mach here, M1. The slope of this curve is controlled by M1. If M1 is too small, there will be no solutions. And we need M1 to be at least such that we have an intersection. So when you decrease M1, you go this way, and if you decrease it too much, there is no solution to your problem. So typically, if you have a slope like this here, there cannot be any detonation. So you see, right away, before doing anything else, you can say a detonation has a minimum speed. If you go slowly, it's not for detonation. If you go fast, more interesting. The other thing you see is that when you move M1, at some point, it will be just tangent to the green line. This point is the famous Chapman-Jouguet point, okay? And we will actually show in a minute that this is the place where most detonations will take place. Not all of them, but most detonations will actually take place at this value here. Now, oh, quite. Going on here. This thing is going too fast for me. So now I just wanted to show you a picture of Chapman and Jouguet. I mean, the guy who did this job, and an Englishman and a French guy. There were only English and French guys at that time anyway, so doing science. Huh? So the CJ point is the point which is here. Can you find it by hand? You need a computer to do that? No, you just need your hand and a paper. You remember that, you know, a paper and I'm not sure. How many have one in their bag? Huh? Not that many. Huh? So you just write here that you want the intersection of these two things at the tangent point here. So you write that the derivative dpdv of this one is minus m1 square, and you do the same thing for this one. You say they are equal, and bim, you find the Mach number. Square root of q plus square root of q plus 1. Isn't that simple? So it tells you that the Mach number of the detonation at the CJ point will be square root of 10 plus square root of 11 or something like this. Now, once you have it, of course, you can replace it in the others, and you can find the pressure jump and the density jump through the flame front. And you find that P2 over P1 is equal to this expression, and ρ1 over ρ2 is equal to this expression. And again, you see it's amazingly simple, considering the animal that you are trying to capture here. Now, we can even do better. Since Q is a large number, you know, you can cancel the 1 here, so you have 2 Qs for pressure, and for V, you have this expression here. Quite simple. So you can go back to the pressure jump. You see that the pressure jump will be this expression, and the density jump will be this expression. Of course, this is a very simple explanation. You can do much better. If you read the book of Lee, you will see you can do much more complicated by taking different CPs on both sides, gamma, etc. But the idea remains the same. So now we have defined the starting point. That's the fresh gases. That's the place where the detonation will arrive. And the arrival point, which must be the CJ point. An interesting question is, how do you go from one to the other point? In other words, how do you go through the detonation? You can understand the structure of that by noting that detonation is a shock followed by a flame. In other words, if you sit in the fresh gases, or you sit in the detonation, or let's sit in the fresh gases, the first thing you will see is the shock, okay? And you go to the shocked state, and after that, you burn and you go to the burn state. Why is that a reasonable description of detonations? Let me show you here this picture. So you are in the cold gases. Beam, you hit the shock first. Through a shock, your temperature goes up. And then suddenly you say, whoa, it's hot here, okay? Chemistry has not started yet because through the shock, you know, a shock is only a few mean free paths. There's no time for chemistry to take off. But now that you're in the burn gases, you say, oh, it's hot, so you start burning. And then there's a flame afterwards. So you see it's a shock followed by a flame. So you can really imagine that you are splitting the flame in two, the detonation in two. First, the shock, and then the flame zone, which means really that the first thing you're going to do is not to go to the CJ point. The first thing you're going to do is to go to the fundament state after the shock. In other words, if you look at this famous curve here where you have the CJ state, you're not going to go from this point to the CJ point. This is not what's happening. First thing you do is you go to the fundament state. So that means the fundament state is here. Remember, that's the line for the shock state, and that's the CJ state. And here there is Q. So the first thing you do when you are in a detonation, you go through the shock. So that means that you go follow this way, and you arrive here at the fundament state. And then after that, you go down to the CJ state. So the pressure goes up and down. Funny, but that's what's happening. So this is the path that you're going to follow. Okay? First you go up, then you go down. Note that the pressure at the Neumann state here is 2 times, these are the theoretical expressions. This was the CJ state, this is the Neumann state. It's 2 times more. So the pressure goes up much more than what you have here. And you will see that this has very important consequences. It's a very high pressure. So there are reasons why people think that the CJ point is where you find most of the detonations. So I'm just going to give you a few reasons for that, because you might tell me, okay, why don't you take the crossing points here and here? You can. There are cases where this happens. But most cases, this one is the right one. So why? First reason is that nature doesn't like, to make too much work. I mean, this is the minimum Mach number for detonation is this one. Why go above it? If this is sufficient to detonate, let's stick to that one. So that's a reasonable reason. A second reason is that if you do the math and you compute the Mach number in the burn gases, again, it's amazing, but you find 1. Which means that the velocity of the burn gases is equal to the sound speed. And this is also something I mentioned initially. When you have a detonation, this is the moment where you have a locking of sound and flame. I just want to show you this movie, which was produced by the team of Elaine Owen. She's really the king of detonations. It's a 2D computation with a single-step chemistry in a channel which is very long. So there are obstacles like this one. There are obstacles here every, I don't know, centimeter. And the tube, would go down the hole here. And we're going to follow the flame. And the flame starts, here. This is hot. This is cold. At this moment, I've jumped a few time steps here. At this moment, this is still a pseudo-laminar flame. You see that pressure is almost constant. Velocity is reasonably small, 80 meters per second. You see that will increase a lot. And as time goes by, this was mentioned also by Moshe this morning, you get more and more winkling on this flame front, so you have more surface. If you have more surface, you are pushing the flame front faster and faster. And as you push it faster, you regenerate turbulence, which increases the flame speed again, and that makes things worse. Now, of course, the transition to detonation will not occur right away. If this is a mine, for example, it will take a long time, but it will eventually happen. As you will see now, you get more and more winkling, and you start seeing that the pressure builds up here. And you see a pressure wave now, moving at the sound speed. And you see that the flame is not yet locked on the pressure wave, but when the two will meet, then we'll go to detonation. That's pretty soon now. After an obstacle, one more winkling, and then suddenly, bling, now you detonate. Okay? And now you see that the Mach number here that you would compute is indeed equal to unity, because 2 waves propagate at the same speed. Finally, there is a third argument which suggests that the CJ point is the right one, is that it's also the point of the minimum entropy for the burn gases. So those of you who remember their thermodynamic courses, you know that PV here It's a pressure density diagram, so you can actually plot an isentropic line there. If you do that, an isentropic line will actually look like this. And by just manipulating the isentropy definition, you can prove that the isentropy line is actually also tangent to the Michelson line. It's here. So in other words, this is the Michelson line, this is the curve, this is the isentropy, and you see that they are both here. In other words, this point also has the minimum entropy. So this is why many detonations will actually be found at the CJ state. So this is the reason why Chapman and Jouguet proposed that, that this should be the point which controls detonations. So I just want now, you see, again, this is theory, but it's not much. I mean, someone doing combustion should know that. I mean, you should not say, oh, it's complicated. No, I mean, you take a piece of paper and you can do it on your own. I mean, it's quite simple. If you follow what the old guys did, initially I tried to do it on my own. It was not that simple. But anyway, let's look at the orders of magnitude of this thing. If you look at the pressure increase here, and you suppose that Q is large, you obtain this expression. And you see that you obtain that pressure increase is 1 plus 2Q over CVT1. And again, if you remember your baseline theory, this 2 which is here is interesting because if you do the same derivation now for a constant volume bomb, in which you have constant volume combustion, you find that T2 over T1 is equal to this quantity. And since you are in a constant volume bomb and whoa cannot change, pressure is also in the same ratio. So you see, theory tells you that if you have a detonation somewhere, the maximum pressure you can reach is this number, generally small compared to that one, so that it's 2 times what you have in the box normally. Okay? But if you do an application for this, so I'm going to take gamma equal 1.3. This is a typical value for QR. This is the initial gases. And this is the CP here. You see that you obtain a ratio P2 over P1 of 19. Okay? While if you would burn these things at constant volume in the same chamber, you would go to 8 or 8.5. So you go to 2 times more. But now that's not the worst thing about detonation. The worst thing is, okay, this is just an example of the temperature ratio and the density ratio. The point is that the maximum pressure is not reached, as I said before, at the CJ state, but it's reached at the Neumann state, which is even higher. So that means if you do now this very simple exercise, and I'm saying that for those of you who are doing experiments, if you do an experiment, you have a box, and the first thing the guys are going to ask you is what's the maximum pressure that you expect in this box before we have, a problem. So because that controls the size of the walls, of course. So simple problem, you have an initial state in your box. What is the final pressure, the maximum pressure that could be reached? Well, if you didn't take a course on detonation, you're going to say, well, it's easy, the temperature increase is given by this, so the pressure increase is given by that. Okay? But if you had a course on detonation, you know that, well, if you have a detonation propagating in this box, the maximum pressure will be actually 2 times that. It will not be homogeneous, okay, of course. It will not, you cannot go to 2 times everywhere. There will be points where there will be 2 times the pressure. And if you wait long enough, you'll go back to 1 if you're still alive, okay, because the factor of 2 on pressure can be a problem. The point is that this is not even the maximum pressure, because at the fundament state, you will go to 4 times that, which is not the same, okay? If you build a box which can resist 30 bar, it's not like 120, huh? That would be, it's not the same result. Huh? So it really means that these are order of magnitudes you can keep, in the back of your head, If combustion is slow, deflagration, pressure will go to P2 over P1 equal 1 QR over CVT1. But if you have a detonation, it will go to 2 times that, and locally even to 4 times that. So those are simple implications. If you take a box which starts at 1 bar, typically you can go to 10 bar if it goes slowly. But if it goes fast, then things will go to 22, and probably there will be a few points where it goes to 44. which is not the same thing, of course, in terms of safety. Now, even if it doesn't last long, okay, a high pressure is a dangerous animal. Just one example where these things are well known, that's piston engines. In a piston engine, pressures, of course, can be pretty high. And the engine is designed to go to 150 bar, you know, diesel engine even more than that. But the problem is that if you consider the top dead center, where you are almost at constant volume, and you start at this moment from a 15 bar up after compression, which is quite reasonable, and you have a factor of 11, you go to 165 bar, and that's okay. Engine will survive. I mean, it's built for that. But if it detonates, that's called knocking. In the old days, you know, in cars, you could hear it. There are two knockings. There's a weak knocking where you can survive, and there's a bad one, which is the one I'm talking about here, where you don't survive. Here, if you have a detonation locally in the engine, then the pressure at CJ will be 330, but locally the fundamental pressure will be 660. That's over, game over, okay? There will be one cycle only, and then the engine is gone. So you find this kind of, you know, engines, and the way you see it in the pressure curve in the engine is that most pressure curves would look like this, and if you go into detonation, bling, you see the pressure here goes to crazy value, and everything explodes. So you see that these very simple estimates are quite useful to understand what's going on in many systems. And of course, this applies, we have mentioned that also, for safety. If you have a building full of gases, if you have a small deflagration, the pressure will increase by a few millibar, 100 millibar maybe. But if you go to detonation, the pressure will go to, you know, 30 bar, and then the whole building is gone. So it's good to know a little bit about detonations if you do combustion. So just a word also, because quite a few students ask me about the computation of this thing. Actually, you can do this thing just again in a very simple way if you understand how it works. Because as I said, you know that the first thing you do in a detonation is you go to fundament. Well, the fundament state is something for which we have an explicit expression. Okay, we know what is the pressure, the density, and the temperature after the Neumann state. There is no combustion, so you just take the expressions I've shown you, and you reach this point. Now you put this point into Cantera as initial conditions, and Cantera will compute combustion. You compute this part here. And so this is how you can, for example, compute this solution. You don't need a sophisticated tool. You can just use one zero-dimensional Cantera solution and the initialization after a shock, and you get this solution. Note also what's happening for temperature. This is temperature after the shock, and here combustion begins, and this is why temperature keeps going up. And this is where you need, those of you who remember the courses on compressible codes, you know that in a compressible code, if the flow is supersonic, if you want to add heat to it, then you have to do something with pressure, and pressure has to go down and not up, which is not intuitive. So this is why you have this funny shape here for pressure. Okay, so you see again this structure, first a shock, then a flame. That's a typical detonation. And then you use Cantera after that, and that will do the job. I don't think you can read a paper on detonation without seeing Chapman-Jouguet, okay? And at the same time, you see how much it is. I mean, it's 5 lines of algebra. And the evaluation of Chapman-Jouguet tells you, you know, if you take Q equals 7 here, that the minimum Mach number to have a detonation is 5.8, so that's fast. 5.8 times 340, that's 2 kilometers per second. So this is the speed at which most detonation will propagate. And if you go now, those of you who are doing RDE computations, rotating detonation, they always compare to this theory. They compare to 3 lines of algebra, but it's amazingly precise. And the other thing I would like you to note is that these results here, and they take only 1 line, they do not depend at all on molecular diffusivity. Molecular transport doesn't play any role there. Okay? It's not important. I didn't even discuss chemistry, because the only thing we need from chemistry is to keep up with the shock, so we need a chemistry which is fast enough. That's all we need to say at this stage. And of course, we can talk about detailed kinetics and all that, but they don't change much of the problem. They will not change the speed. If they're fast enough, what's driving the problem is the Chapman-Jouguet conditions, and that's sufficient. Okay, I think I'm going to stop here for detonation. I just wanted to give you a little bit of background on that, because I suspect you might use it at some point. Any question on detonation? Actually, we can stop for a few minutes if you have a comment or a question. No? Yes? No, because this is a simple computer. Yeah, the question was, the question you're raising is that actually you feel that the temperature jump is too high, and that's right. If you take into account dissociations, you will not go to these temperatures. So here I took 11, that's really the worst case. In most cases, it will be around 6, 7, or 8. So you will not go to 6,000 K. Huh? You never go beyond 2,500 anyway. After that, you get dissociations. Okay, there's a gray zone here where chemists tell you that through the shock, they have no idea what's happening, okay? So you might even have non-equilibrium chemistry, which explains why many complex chemical schemes actually fail in the detonation, because they are lost, you know, it's going too fast. And that's another problem, okay? But here, by the way, we are at the end of the spectrum. This is a much more complicated thing than what I described here. But yeah, you're right. Non-equilibrium chemistry could be an issue here. Yeah.
Like idea of what's the role of radiation at the spectrum? Because it's going so fast. I'm just wondering if it's what the condensed gases that ignite.
Yeah, radiation and detonation. I don't think it's a topic that people look at much. I don't think you take into account radiation when you do detonations usually. They go so fast that I think they don't really care about radiation. You don't have time to worry about radiation. But I would have to check. I don't know any papers who included radiation to do that. Yeah, but again, you see, for example, in the detonation, there is no diffusivity because you don't need it. And I think you don't, even radiation would cool down a little bit the burn gases, but not change the speed of the flame. I doubt that would play a big role. Yeah.
Is there any difference in modeling detonation lower speed?
Yes. So the question is there a difference when you model detonation and deflagration? Yes. Actually, if you go to France, for example, the people studying detonation, that mainly the people doing at the Atomic Agency, their codes don't even have diffusion. They are pure inviscid equations because we know that for detonation, you don't care. So if you work for weapons, for example, you drop diffusivity. So all these models for molecular transport, everything you can forget, all that. You just need to have the compressible effects. And so it is not the same code here, except that when you want to do DDT, which is what I've shown you, deflagration to detonation, you need to do both, and then you need a code which has all the features. But no, it is not the same equations. Actually, you saw in this demo here, you don't need any description of diffusion at any point. Not important. Another question? Yes. Yeah. Yeah, the induction zone is exactly the one I've shown here. Just after the shock, you have a moment where those gases are hot, and so it's a little bit like an autoignition problem. You start, it takes a while. You start combustion. This is here. And the induction length is basically the time it takes for combustion to start, And actually, this is the flame thickness somehow. And this one is controlled by kinetics. Okay, if the kinetics are slow, you're going to be too way long. And this is where you tune your kinetics, and the induction length is this typically the distance you need after the flame so that this thing can start burning. And I didn't go into that. After that, this thickness, of course, will be important because it controls the size of the cells which develop on the flame front. And so when you match a chemical scheme in a detonation, you match the induction length. That means you match this distance here. Yeah. Yeah, absolutely. You can tune the pre-exponential constant. The funny thing about the people doing detonation is that that's the only thing they do. They don't do complex chemical schemes. They know the size of this from other measurements, and they just tune either the pre-exponential constant or the activation energy to have the right size. So this is an ad hoc process to find a chemical scheme. And if you talk to Elaine, she will tell you, yeah, sure, it's not very good, but it's not useful to do better, because in this zone here, chemical schemes get crazy. They don't understand what's going on here. You see, remember, the temperature went up like this, so for a chemical scheme, it's just too fast. That's an open discussion. The funny thing also is that today, if you do these simulations of detonations with a single-step chemistry, like this one here, and you say, oh, it's not good, let's put a complex chemical scheme, the results get worse. And this is the only example I know where things get worse. For deflagration, when you increase the quality of the chemical scheme, things normally improve. Not for detonation, which tells you that there's something funny about chemical schemes in detonations. The results get worse. You don't get the right size, you don't get the right speeds. The structure is not as good as the one which you have with a single step. Of course, it's not really fair because the full scheme, you don't tune it, while the single step, you tune it until you find what you like. But still, most people computing detonations, they don't want to go to too complex schemes. Yes?
With regards to, this is almost like a DBT question, but the auto ignition has kind of been, at least for the more detailed chemical reactions, has more or less kind of been put into question. What do you think the likelihood of it being with regards to more turbulent codes, trying to take into account flame collisions, with regards to using detailed chemistry to look at either flame runaway through a non-auto ignition mechanism or through the Zeldovich mechanism?
Okay, if you're talking about transition to detonation through the Zeldovich mechanism, clearly, well, we haven't talked about that yet, huh? Because okay, there are two different worlds. If you have a fully established detonation, okay, you can do things. But if you want to compute the deflagration to detonation processes, then you need to be precise in the deflagration phase. So you need complex schemes which can predict autoignition, especially for the Zeldovich mechanism, which makes your life more complicated. And then you have to pay the price for that. And that's difficult, right? Because if you, for example, if you want to do that, you need a complex chemical scheme in a flow which goes to detonation, which has steep gradients. And if you need to do that in 3D, today it's almost impossible. It's really difficult. That's what people try to do in engines, typically. In a piston engine, when you go to detonation, you have this type of problem. And again, today it's an unsolved problem. Yes?
How do we know that the state of the gas goes to 1 point?
Yeah, well, we know it because they have pressure measurements. So you can, but again, as you've seen, the Neumann state is really small. Huh? It doesn't last long, and it's a kind of it's a small zone in the flow. So to be sure that you see that, you need just pressure measurements, precise high-speed pressure measurements. And that's actually one of the problems. For example, in the engines, initially, they did not understand why they were breaking the engines just because the pressure sensors were not fast enough. I lost it. Because you need a very fast sensor. But if you have a very fast sensor, you will see it. You will see that this thing goes to a very high pressure. Yeah, in this kind of data, for example, here, it's difficult to build a pressure sensor which can react on a few mean free paths in terms of space, which means in terms of time, it must be microseconds. Your pressure is low and suddenly boom. So it's difficult to capture. But I think everyone agrees that you're going to von Neumann, maybe not exactly, but you're going very close to it, which is very high. A question?
So for, I can understand that we have three ways to calculate maximum pressure. Slowly, kg, and then you measure when. I don't know why, because the energy is the same, when pressure is different.
Yeah, but that's what I said. Of course, the total energy is the same. The difference is that when you burn slowly, it's the same everywhere, it's homogeneous. And when you have a shock, it's less here and more at the flame. And so again, on average, it's the same. But if you are sitting at the point of maximum pressure, you're in trouble. Huh? Yeah, it's really, if you come back after a long time, everything will be the same. But it's really during the transient phase that the shock will be important. Okay. Okay, let's move on to the next topic. I think I'm going to start with hydrogen. Actually, it's a fancy topic at the moment. So just before the break. So this is a big issue, okay? Maybe not as big in the States as it is in Europe, but to give you an idea, I was counting yesterday. I will have 21 PhD students working on hydrogen in September. This is just out of control. So, to understand why, first, I need to go back a little bit on energy policies. I started by that on Monday, but I want to be a bit more precise here. And then I will talk about H2. H2, there are basically two big classes of problem. One problem is to make the engines and all the system we use work with H2. And the second problem is we don't want to die in the process, which means safety is an issue with H2. And and these two things are combustion issues. And so they will come into our community, and you need to do something about it. So before I go there, I just want to know, who knows the name Jean Covici here? No one, huh? He's the French guys probably, yeah. In France, he's quite famous. They were thinking of him to become a minister. He's a guy who has two things. He has a company who is doing your CO2 balance, if you want. And he has a project called the Shift Project, which has been thinking about global change and energy for a long, long time. And one of the nice things he's doing is to try to illustrate things for people in terms of energy. And the first thing I introduce is what we call the N number. The N number is the number of humans working for you to provide your energy, okay, full time. So for example, here, you see 200 years ago, you had these guys working for himself, plus a few animals, which were not working full time. So typically here, if you would wonder what is the N number that this guy was actually using to have his energy, you would find something like maybe 2, you know. Himself, not full time, these 2 animals, well, maybe a few kids, PhD students, I don't know, which is not much, okay. So today, what Jean Covici explains is that we have replaced all these animals by machines. And the interesting thing is to know the order of magnitude. If you look at all the machines working for us, they increase, of course, the energy. Right now, at this moment, there are quite a few animals working for you, okay? Electricity, heating, whatever, AC, the cars to come here, the projector, whatever. So what do you think is N today? How many people are working to provide your daily energy? That's something that people actually, they don't realize that. On average, it's 200 over the whole world, but of course it's not homogeneous. It's about 600, 500 in France, 1,000 in the US, and the country which consumes the largest amount of energy per person is Iceland, 4,000. So, because they have a lot of free energy, you know, just dig it out of the ground. So what does it mean, really? It means, you know, if you live in the United States, at every moment of your life, there's the equivalent of 1,000 guys working for you to provide your energy. And the energy comes from everywhere, okay? Energy to produce this chair, energy for everything you eat. I mean, it's just integrated. And so you see that when people talk about diminishing or stopping, let's stop combustion. Okay, well, then you have to find 999 people to work for you, because this will stop right away. And so, of course, this is a major problem. And also, this energy is, as you know, provided mainly by combustion today. And so we have quite a few challenges in front of us. So also, Jancovici explains things like 200 years ago, everything was renewable. There was only wood, okay? So that's fine. I mean, if you don't burn all the wood, okay? But normally, wood, 150 years ago, was our main production of energy. It's actually going down today because we don't need wood that much. And then we started burning coal, which may be not a good idea, but we are burning coal more and more through electricity, to do electricity. And you know that we are opening, you go to China, you are opening a new one, I don't know, every week or something like this. So, and actually Germany is reopening coal power plants today. Then we introduce oil, and oil is really used for transportation. Then we introduce gas. Then we introduce hydro, this blue line here. Then we introduce nuclear, and then we introduce renewables. That's renewables, okay? So you see the problem here, that this thing is really too small compared to combustion. And it's not our fault, okay? But that's the way it is. Huh? So we know that we need to do something. And to minimize our fossil fuel combustion, we need to go to renewable. Everyone understands that. But renewables are intermittent, so you need to store them. And this is where H2 comes into the picture. And I've shown you that before. One solution is these power-to-gas solutions, where you use the renewables to produce H2 using electrolysis. And this H2, you can store it and recover it later, as late as you want, actually. Yeah? Now, I will not come back to that. I talked about it on Monday. So you suppose now you got all this H2. Today, it's not the case, okay? Today, 99% of H2 is produced with oil, okay? It's not green at all. But suppose we can do it. What can you do with this H2? And this is where the business comes back to us, okay? You can, of course, use it in a fuel cell, and there are fuel cell cars, you know, in many places. You can convert it to, you know, CH4 or ammonia if you want to store it easily, but you can do many other things. Once you have this H2, you can just burn it, okay? No need to be sophisticated. You could burn it in a modified piston engine, but there are many piston engines working with H2 today. I mean, it's a standard procedure. There's a small problem with NOx, but it's something we can fix. You can burn it in a gas turbine for power generation, and this already works. You have gas turbine doing electricity with 100% H2. But you can also do things which are a little bit more radical, like the one I've shown you for RDEs, you know. You can imagine new engines with rotating detonation engines, for example, because it's kind of difficult to make kerosene detonate. But if now I tell you, you get all this H2, combustion experts will say, oh, that's nice, maybe I can use it to do a different engine. And RDE, of course, would be one solution. Porous burners is also an exciting solution to use H2. And that's, again, your new science for you guys to develop. And then you wouldn't believe it, but we do other things with H2. Of course, we burn it in furnaces. But in barbecues, there's a huge market for barbecues. It's a typical American market, and Japanese, actually, that they want to have a clean H2 barbecue and go there with their SUV, but that's just, I will not comment. In any case, for us, there's a huge business in terms of scientific problems there. By the way, you will say also from an engineering point of view, you know, it's going one day Monday everyone's burning CH4 and Tuesday everyone's burning H2, it's probably not reasonable. So there will be a lot of cases where we will actually mix H2 with other fuels, whatever they are, okay? And now from a scientific point of view, you realize right away that mixtures of H2 with other things are going to be fun. You think, for example, of ammonia H2 mixture. Ammonia flame speed 7 centimeters per second. H2 3 meters per second. We mix them and we let them burn. It's going to be fun. I mean, it's going to be very interesting in terms of flame structure. So there's a lot of work to do. H2 is not actually the only one. H2 is only the entry gas because when you do electrolysis, you recover H2. But then, this H2, you can do a lot of other things. Of course, you can do what I just said. You can burn it. But, you can, do all these things with it. Chemists can do anything. It's just a matter of money to know if it's worth doing it or not. So there's a huge place here for research to know how to best use H2 in the future. Now, of course, there is many of us are working for aircraft because that's a place where we need advanced research. And there's, of course, a question now, which is, what about aircraft and H2? And so there, things are a little bit more complicated. You know that the Americans don't seem to believe too much in H2, while the French and the German are like crazy about it. And to tell you, just to give you an order of magnitude, in Toulouse at the moment, there's a team of 500 people designing an H2 aircraft. Okay, they are just going for it. Actually, not for it, they planned 3 aircraft working with H2. So why? You get this usual picture, you know that the aircraft companies are in a bad situation when it comes to climate change. And so they have pledged to go to a situation where they will diminish them by 50% so that they will become almost neutral in 2050. And the question is, how do you do that? Well, there are many ways to do it, but it's a huge number, okay? And it's a huge negative number. If we don't do anything, that will go up and up and up. And at some point, the public will start saying you have to stop flying. I don't know about the States, but in Europe, many of my colleagues don't fly anymore. Just the symposium in Vancouver, they don't go because they don't want to fly. If you cannot go there by train, they don't go. So in Toulouse, we sell aircraft, so we think it's a bad idea. So, of course, one solution, but there are only 2 solutions. So if you talk to Airbus, they will tell you there are only 2 solutions. They have looked at everything, ammonia, electric, whatever. There's only 2 solutions, SAF, synthetic fuel, or H2. Those are the only 2 solutions which on the paper have any chance of going through. SAF, because this is kerosene, okay? You just don't change anything. You just get the kerosene from a synthetic system. The other solution, which is more fun, of course, is H2. So to do that, you need H2. So by the way, for a scientist, the first time, actually, the French president went on TV to say we're going to build an H2 aircraft. All the scientists in France said, oh my God, what's it? First thing is a small detail. How do you bring the H2 on the plane? How do you carry it? Well, there are not that many solutions. Huh? Either you can put it in a big tank, or you can put it in a smaller tank, cryogenic tank. So some people were complaining that COVID vaccines were difficult to move because they had to move at minus 80 degrees C. That's the international unit, by the way, not Fahrenheit. Don't forget that. But here you have to move it at 20 K. Okay? That's the temperature at which H2 is liquid. So cryogenic, what's interesting, of course, is that you know that H2 is much more powerful for 1 kilogram than kerosene. So typically, if you want to fly a big aircraft, which had like 220 liters or cubic meters of kerosene, you can replace it by only 80 tons of H2 instead of 200 tons. But the problem is that even when it's liquid, it's not very dense. Okay, you see it's 70 kilograms per cubic meters for H2 liquid, while it's 800 for kerosene. So that means the tank would be 1,000 cubic meters. That's a big tank, okay? 10 by 10 by 10 at 20 K. It's interesting. Okay, so some people said, nah, now we're going to do it pressurized. Well, pressurized. Pressurized, you would need to go at least to 700 bars. to have a reasonable density, because remember the density of H2 is so low, okay? The P equal rho RT, the R is enormous because the W is very small. So we know already what's needed for these tanks, you know. It's very difficult to make them, but even if you make one in this Toyota car, you know, which is running at the moment in different places with H2, the tank is about 130 kilograms to carry, I think, 7 kilograms of H2. So now suppose that you need to carry not 7 kilograms, but 80 tons. You know, of course, you can maybe, but no, it doesn't work. So the conclusion of Airbus was it's not going to be pressurized, it has to be cryogenic. But once you have said that, you realize that it is not going to be simple. So for us, if we talk only about the engine and not about safety, the first issue is if we need to burn H2, can we just unplug the kerosene and plug the H2? You know? No, it's not going to work, as you know, because H2 is very different. The first thing is that it leaks a lot. So all the lines have to be changed, okay? If you talk to Airbus people, they'll tell you there will never be any duct like this to transport H2. Everything will be doubled, so that if it leaks, you have a chance to catch it up later. Okay? Otherwise, there will be too many leaks. The other thing, of course, is, and you had a course on that, hydrogen ignites very easily. And I will give you some numbers in a minute. And of course, it burns much faster than all of the fuels. You know, we talked about it many times. A typical flame speed for fossil fuels, normal fossil fuels, is 40 centimeters. For hydrogen, it's 3 meters per second. And so a factor of 10 is not something that you can avoid. And of course, hydrogen is the best one if you want to make explosions. So quantification of that, you know that the lean flammability limit and the high flammability limit, and you see that the problem with hydrogen is that whether you have a little bit of it or a lot of it, it burns, okay? Which is not the case with propane or methane. So hydrogen, as soon as you're leaking hydrogen somewhere, it's very easy to ignite it. And it will also not require a lot of energy. Remember, we talked about the MIE yesterday. The minimum ignition energy for hydrogen is very low. So it doesn't need a big spark or a big anything. It will go easily. So it will go in a wide range of concentration, and it will go for a wide range of sparks or anything. You can actually ignite it against a hot wall, for example. If you think of an aircraft in the engine casing, there are many hot surfaces around. So if you arrive there with hydrogen, you don't even need a spark. So that will require research. So you will have jobs, okay? You move to Europe. Actually, Airbus is hiring people so fast that the human resources of Airbus went on burnout. They could not hire people fast enough. So I think they hired 800 engineers in 3 months or something like this. So that's the typical flame speeds now. Methane, as you know, 40 centimeters per second. Hydrogen, pure hydrogen, and all the mixtures in the middle. Remember also something funny about hydrogen is that the peak velocity is not obtained at stoichiometric condition, okay? It's obtained at 1.6, something like this. This is where you go to the 3 meters per second. So it is definitely a strange fuel. Now, of course, at the speed at which things move, especially in Europe at the moment, there will be hydrogen everywhere. Okay, probably you don't know. Who knows Ursula von der Leyen? The Europeans. Who knows Joe Biden? Okay. Ursula von der Leyen is the president of the European Union. And she said 2 months ago, Europe is going to stop buying and using Russian gas, and we're going to replace it with hydrogen. So again, everyone in Europe said, oh my gosh, why do we have to do that? You have to imagine you're burning CH4, and suddenly you have to move to H2. Okay, no, but anyway, that's the plan today. See tomorrow. So there are 2 problems to do that. The first one, as I said, is that you're going to have to redesign the tanks, the lines, the pipelines, and all the combustion systems. furnaces, engine, whatever, heater, everything has to be adapted to H2. And again, it's not, with this difference, you cannot do it like this, you have to change a lot of things. And the second problem is that we have to do that so that it keeps, it remains safe. And as you have seen, the safety of H2 systems is really not the same as the safety of other systems. And I will give you a few reasons for that later today. Again, the difference compared to before is that numerical simulations here will be essential. What we see at the moment in Europe is that everyone is running to have the first aircraft flying with H2. So they do it with a new strategy now. That's what they call cutting the corners, and the way they cut corners is by replacing tests by simulations. And this is, after this course, I guess you guess why I'm a little bit nervous when they come to me. We are going to replace this test by a simulation with your code, okay? But I'm not signing anything because, but anyway, because their plan is to fly in 2 years, okay? Which is just normally you take 5 years, 8 years, 2 years they want to fly. So, of course, the idea is that we probably sold them too much. We've told them that we had these digital twins, That's the digital twin is like the AI, digital twin is you can run this thing virtually and then the real machine will work exactly in the same way. I mean, they can believe it, we don't believe it, but that's just... it sure makes nice movies, okay? We are actually computing this engine now completely. We are computing the compressor, the engine, the chamber, and the turbine behind it. Everything goes together. And it is true that it is as close as possible to an engine. But of course, I mean, it doesn't compute the temperature in every blade or, the oil distribution. So it is useful, but it's not what we call a true digital twin. I mean, no one can believe that. And the idea is now they ask us, okay, now you replace kerosene by H2, what's happening? Okay, well, it's a good question. So why will the engines have to be different? Initially, there was this misconception of people saying, because H2 burns so fast, it will not be a problem to make combustion chambers with H2, okay? If it goes fast, then it's easy to burn. Well, in practice, it is not like this. In your kitchen, for example, you're burning CH4, you can add a little bit of H2. You can go to maybe 10%, maybe 15%, but after that, no, it's not going to burn. You will have flashback, you will have problems, and everything will melt. So if you want to burn H2, if you want to go to 100% H2, you have to replace all the combustion systems by other systems. And I was talking, actually, Alison Tomlin lives in a city, Leeds, where they plan to move completely to H2. And then the problem is, how do you do that? Because you have CH4 on Monday, and Tuesday you have H2. Well, you have to change everything during the night, or you have to have systems. This is where it gets interesting for combustion people. You have systems which can do CH4 and H2 at the same time in the same engine. You just flick something, and then ping, it can burn one or the other. But that, you have to invent them, because if it works for CH4, it doesn't work for H2. You will have to change something in the system, and that's not so easy. So if you want to go to pure H2, you need to change a lot of things. And all the tests that we see today, and probably the most advanced are the power generation companies. They can make it work for H2, but it's a tough job. Okay, it's not simple, and many turbines actually don't do it. You cannot make it in many turbines. Some of them you can, and others you cannot. Why? Well, because usually, you have problems of thermal loads on the wall, or you get into combustion instabilities, you've seen yesterday. You make also a lot of NOx. I will explain you later why. You can have violent ignition. I talked about that also yesterday. It's not easy to ignite an engine with H2. You can have surprises. You can have flashback. I've shown you examples too. And of course, because the power of H2 is very high, you usually have a lot of noise. Those are very noisy flames. In the lab in Toulouse, when you operate the H2 flames, you recognize them. They scream more, and they scream at higher frequencies because the time scales are shorter. You know, every time you have a more intense flame, then you have more noise. Okay, I will continue after the break, but maybe we can take a few questions now if you want. Yes?
From a computational and
Okay, if you, the question is, what do you have to do from a CFD point of view for the equation of state? Yeah. H2 is a great gas, it's a perfect gas. So as long as you don't go to high pressure, we'll stick to the perfect gas equation. That works. Yeah. You have to change when you go in a rocket engine to 120 bar. You have to move to a nonlinear state equation. But for most applications, we can stick to P equal rho RT to work. Yes? Yeah. There are people working on breaking ammonia on board for cars. People, I think Airbus gave up on ammonia anyway because it's too heavy. You carry all this N for nothing. But for cars, certainly, it would be better because no one wants to have two tanks in his car, one for ammonia, one for hydrogen. So it would be convenient to have one tank for ammonia, then to break it a little bit into H2, and then to do an H2 NH3 flame. But I don't think it's going to fly. I think it's going to go on the road or on the truck. But NH3 is too heavy to fly. And again, when I say too heavy, it doesn't mean you cannot do it. It means that when Airbus does the whole analysis, including the price of the ticket and how many people they can put on an aircraft, they say it's not going to work. There will be 2 passengers. So it's not efficient. No one will buy it. But the nice thing, actually, that Airbus is saying is that it's the request for clean green aircraft comes from the companies. Every company now, they feel that even you, the customers, pretty soon are going to look at aircraft and to say, we want to fly in a green aircraft. You can always paint it green, huh? But that's not what I mean. Actually, I heard that the 380 Airbus are coming back into production, into action, because they are actually saving fuel. So these huge aircraft are coming back into the picture. Other question, yeah?
So the first question is, do you think the batteries, lithium batteries are a viable alternative, like competing against hydrogen and US is better than that? The second question is, I think GE and Siemens does have like 50% hydrogen X series gas power plants. So how different are they and like how different is their engineering from usual?
Oh, well, Siemens and Alstom, they all have 100% H2 gas turbines today. Not all of them. If you're a customer, you go there, they will show you, for this one you can go up to 50, this one to 80, this one to 100. So they have technology to go to 100. Now regarding batteries, the point with the batteries is the number I gave you initially. You know, 1 kilogram of H2 is probably like 80 kilograms of batteries today. And so this 80 may become 70, but there is no evolution. The laws of physics tell you that the batteries won't do it. So Airbus just erased the battery solutions there. It won't fly. Again, it will go on the road very well. We see that every day, but flying is a different business, okay? You have to take off. Right? It doesn't work with a Tesla. Huh? SpaceX, yeah, but SpaceX is not using a battery. Another question? Okay, we take a small coffee. We'll be back in 15 minutes. So I just want to finish the H2 talks, and then I will talk a little bit about Flammal Interaction, which is a fun topic to finish with. And then you'll be done. So just since we talked about CFD, there's one nice thing about CFD is that H2 is simple. Okay? That's the only fuel for which we have a full scheme at almost no cost. That's the only good news for CFD. There are also no drops, no problem of two-phase flow combustion. So that's good. The problem is that a lot of people will want to mix H2 with other fuels. So that's bad. If you want to mix H2 and kerosene, then we again are in trouble. But still, it could be okay. So I want to talk about 2 examples which are quite important at the moment. And that's the way we are redesigning engines, okay? Your job is you take this engine, and we're doing it at the moment with multiple companies, change the kerosene or the CH4, make it work with H2. What should I do? Well, it is actually, I'm going to take two examples, Cranfield and IMFT, where I'm working, and it really comes back to things that you should master now, which is mixing versus burning. In other words, premixed flames versus diffusion flames. When you burn methane, or most other fuels, which have a speed of the order of 40 centimeters per second, you have this chance that you can actually mix things rather fast before you burn them. So in most cases, you have a mixing zone here, for example, in the swirler or in front of the swirler, and then after that you get combustion. And this combustion zone is mostly premixed, okay, which means mostly efficient, which is not the case when you go to hydrogen. Because with hydrogen, H2 will, with the existing systems we have, burn so fast that it will swallow the mixing zone and stick to the injection. In other words, it will do a diffusion flame. And if it does a diffusion flame, we'll have problem of heat load on the injector lips and too much NOx. Remember, we talked about that. Diffusion flame equal high temperature equal high NOx levels. So that's not good. We want to avoid that. So how do you do it? Well, it's a problem when you mix now fluid mechanics and chemistry. Chemistry timescales you cannot change. It's hydrogen. So you need to manipulate the flow now to make things fast enough. You could say it's not a problem for rockets, for example. Why is it a problem today? Well, when you look at a rocket with H2O2, for example, you definitely have a diffusion flame here. While if you look, for example, here at a torch with methane, this is the reaction rate here. You see it's not a diffusion flame. Figs mix, and then they burn. And it is true that for H2O2, all the flames were diffusion flames anchored at the lips of the injection, while the classical flames are lifted. In other words, those flames here on top are diffusion flames, and those at the bottom are clearly premixed. But the point is that in a rocket engine, you don't care about NOx, okay? You don't even care about the lifetime, okay? Because it's not a problem. But now we have to, if you go in an aircraft, it's a different problem. We cannot live with diffusion flames. So how do you know if a flame is a diffusion flame or not? You compare, the famous Damköhler number. You compare the flow timescales. Those are the typical flow timescales that we have. And if you put here H2O2, H2air, and CH4air, CH4air, they have a long chemical timescale compared to the flow time, so that you can indeed do something which looks like a premixed flame. While on the other hand, here, H2O2 goes so fast compared to the flow that you have diffusion flames. And the problem for H2air that they are just in the middle. You can have premixed and diffusion just here, and I will give you an example in a minute. So we don't want to work in a diffusion flame, so we need to manipulate the flow now, and this is a direct indication that we need to change the engine, or at least the injection systems. So how do you do it? Well, one idea, that's the idea that Cranfield has proposed, is to increase mixing by using very small jets of H2 at very high speeds. And you see the idea here is that if it goes very fast and it has a very small section, it will mix rapidly, and then it will burn later, so you can, probably do it. So you have this jet of H2 here with a jet of air in cross flow here, and you hope that normally you will mix, and then later you will burn. That's what you hope. Which means also that if you start doing that, you have to replace the existing systems, which are these swirlers here, by a lot of small jets like this, okay? So it's a complete redesign of the chamber, and Cranfield is working on it at the moment, and it's quite an ambitious project in Europe, where they actually built, atmospheric and high-pressure systems to test all these things, because it's complicated. We do it in a different way in this European Research Council contract here, which is one of the biggest contracts you can have in Europe. And we have developed another system, which is called the dual swirled injector. And the idea here is in this system, it looks like a classical system, but you swirl the air and the hydrogen in the center. And when you do that, it gives you a way to manipulate the mixing here so that you don't have diffusion flames. And that's actually quite a sophisticated tool to develop. Let me show you just a view of the flame. you know, the first thing you see when you look at this flame is that it is blue, okay? So it is close to a, well, as close as possible to a premixed flame. So these flames, when you operate them, they come in two classes. The first class is here, and you can recognize here, this is the injector. You see this zone here, that's a diffusion flame, so that's not good. Okay. While this one has no diffusion flame at all, it's lifted. So this one we call attached or anchored, this one is lifted. We want to operate here. When you measure the NOx, here for example, or the temperature of the lips, it's not good. You don't want that, you want that. Because here you mix and then you burn. So the whole problem is how do you do that? Well, if you look at a map of operations here, you have images of these flames as a function of the conditions of operation, the power and the flow rates. You see that when it's green here, it's a good, what you call a good flame. It's lifted. So you could operate that in an engine. And then when it's red, it's not good because you have diffusion flame, the NOx goes up, and that you cannot operate the system like this. So everything should be green, which is fine in the lab, and also everything should remain green at 30 bars, which is more difficult. Okay, when you go high in pressure, again, other things may happen. And also you must, when you do that and you develop this for industry, you must be able to tell them when they will have the right operation and when they will have the wrong operation. You must be able to show that you will be able to ignite the engine here and not have to, you know, play around with this kind of flames. So this is an ongoing work where I'm just going to show you a few results here. You do LES for that, if you have to believe in LES. Just to show you the type of accuracy, I haven't shown that yet, but this is a typical result when you do LES. When you do cold flow LES today, if you're not right on the experimental data, it's that the experimental data is wrong. Okay? Because LES without combustion today in those systems for swirl flow works extremely well. You see here cuts of velocity, UZ at different places. You have the symbols and the lines of experiment and LES, and you see they agree extremely well. And even when you look at the IMS values, so those are the perturbations, you see that the agreement is extremely good. You can never obtain that with RANS, okay? Don't even try. It's just, actually, RANS doesn't know the difference between Z and R. You know, if you use the K-epsilon model, you cannot do it. You have only K. So now, if you go to hot cases, you can do PIV there to measure the velocity field. Again, that becomes a little bit more complicated experimentally. And then you can compare in different planes, LES and PIV, and you obtain the, the classical result. Not so good here, not yet. You have the LES and the particles. The problem is that the particles here were too big. For those of you who do PIV, it's not an easy game with hot conditions. But still, we are pretty close to the experiment. And if you look at the IMS values, I mean, they are also very close to the experiment. So what I want to show you that is that LES for this flow captures the regimes, but it also captures the transitions. This is, for example, what we call flame A. It's an attached flame. You see it from the back here. So you have the injection and the swirler of hydrogen in the middle and air here on the side. And you see the flame is attached to the lips here. So that's not a good flame. And you see the flame surface here colored by the velocity. And of course, like always, it makes nice movies. Not sure that it increases the scientific quality, but at least you visualize what's going on. You see the flame is stuck here to the lips. It's a diffusion flame for this case. While if you go to a lifted flame, you see now for this case, LES actually shows that the flame is not anchored to the lips anymore. The flame is sitting somewhere here. And if you look at its characteristic, you see it's a premixed flame. It makes much less NOx. And the lips here of the injector are much cooler, which is, of course, better for the lifetime. So you can compare the experiment here and the simulations. And you see that the simulation captures really well the zones where you have diffusion and the zones where you have no diffusion. By the way, this means that the model that we use is able to capture at the same time premixed flames and diffusion flames. And I told you yesterday probably that this was difficult. Why are we able to do it here? Well, because we cheat a little bit. Here in this zone, we are actually doing DNS. The resolution is very high, so there's no problem here. It captures what it should. We do LES only in the premixed zone, but the lips here, everything here is very highly resolved, because otherwise we wouldn't trust the results. Remember what I said yesterday? Having a model which does both diffusion and premix today is really tough. So that's the difference between the two flames, okay? This is anchored. You see the flame is touching the lips here, so you can imagine the temperature here and the reaction rate is here, while when it's lifted, it's sitting here in the middle of nowhere, and so that's much better, and it's also what we see in the experiment. Those are the ISO contour of temperature. And of course, like always with LES, once you believe the LES, you know, you have everything you need to analyze this flow. So that's good. Now, I want to show you also that the LES can be used to understand how the flame moves from one place to another. So here we're going to start from a lifted flame and change the flow rate, and you're going to see how the flame actually comes back to stick to the wall. So the flame initially is lifted. That's a good regime here. And then we decrease the flow rate, and you see that the flame comes back and attaches to the lips. So that's not good, okay? And so the main discussion at the moment, we are installing this system into an helicopter engine, and the main problem is that you never want this to happen. And by the way, also, this is where things get complicated. If you take a good postdoc, the guy will ask a question, which is, does the conclusion depend on the mesh? Which is a question you should never ask, because quite often the answer is yes. So I'm going to show you now the thing we didn't show to them. It's just, well, we mentioned it. I'm going to show you the same computation with a finer mesh. So here you get the coarse mesh on the left and a finer mesh on the right. And you see that you have reattachment on the coarse mesh, but not on the fine mesh. And this really comes back to what I told you yesterday. It's easy to do one computation one time to get one movie. But if you want to be able to bet that you get the right result, then things get complicated. You see here, this one, you would conclude that it's reattached, and this one you would not. So when you reach this point, you say, okay, you cannot increase the mesh more. I think this is already 100 million, so it's difficult to increase it. So now you have to say, what do I believe? And this is where you have to be very careful with your LES. Okay, this was for pure H2. But many people, as I said, don't want to move to pure H2 tomorrow. There's a very interesting thing, for example, is that the regulations for emissions for your heating at home, the CO2 levels are going down every year. They are not going down like this. They're going down slowly. So the idea of the gas turbine, not the gas turbine, the heater manufacturers, is to add a little bit of H2 every year, you know, to decrease the CO2 emissions. So you start with 100% methane, and then you decrease it, and this way you can at least satisfy the regulations, because again, you cannot imagine you're going to change 50 million heaters, you know, like this. It's going to take time. So if you can retrofit somehow systems to use a little bit of H2, it will be useful. So you can replace or you can mix. Mixing is actually a realistic solution. And also, even if you talk about aircraft, it's the same problem. Even if you go here to a pure H2 aircraft, in the middle you might have to do something. And there are other strategies where you start mixing two fuels. So what I want to show you now is chambers where you keep the fuel that they have and you add one line of H2. Okay? And that gives you, in terms of control, a lot of flexibility, because you can modulate the fuel flow rates the way you want. And this is a typical example here. You have an existing chamber and you fit an H2 injector somewhere, anywhere. And then you can, you know, start playing with that. You can make it work from time to time. You can make it steady, or you can pulsate it. And you can even ignite it, for example, when you have problem of quenching. Or you can do a lot of things in terms of controlling this chamber. So I just want to show you an example of how this would work here for a chamber that we have, where we have a CH4 air mixture, premixed, entering the system here by these two holes. And here in the middle, we have a very small tube where we can add hydrogen. And you will see we add a little bit of hydrogen, maybe 2%. And this is where things get complicated. This is a view of the chamber. So again, remember, this is premixed CH4 air, and in the middle, we can add hydrogen. So this is a view of the flame. As you know, one of the main problems of combustion is to be able to operate as lean as possible. There are many cases where you cannot because the flame quenches. This flame here, I'm going to show you a regime when it's almost going to quench. You will see it's, it's up on our, and then it's hesitating. Then we add 2% of hydrogen here, and then we stabilize the flame completely. Exactly like what I've shown you with the plasma a few days ago. So look at the results here. You see this flame, it's almost quenched. Then we put hydrogen, and then it's stabilized. So you see that by just putting 2% of hydrogen in this system, you're able to bring the flame back where you want it. And the other thing you don't see here, but we did it too, is you can look at the operation of the system. This system, like all flames, has problems of noise, okay? It's making too much noise in a wide range of parameters. When you add a little bit of hydrogen onto it, all this noise goes away, which means really that you can operate the system here. You may even be able to operate it even for leaner conditions, okay? Which means that you add a little bit of hydrogen, then you can remove also a little bit of CH4 in addition. So that opens for, again, for us, quite a new field. As soon as you can use two fuels for the same chamber, you can do quite a few new things. And you have a lot of requests from companies to do that today. So, of course, again, that's the problem we always have with people interested in ecology. When you say combustion is bad, there are two things you can do. You can stop it, or you can improve it. We improve it. Those guys want to stop it. Stopping it won't work, okay? So even if you improve it by 10%, 15%, it's better than doing nothing, and it's better than having people fighting in the streets because they cannot buy fuel anymore. So I think this type of strategies also have a place near the other strategies of using pure H2. We'll see mixtures of H2 with other things. Okay, let me go back now. I talked about the aircraft, but this is actually applicable to all H2 systems. What about safety? That's a big topic. Safety for H2 is an enormous question. If you talk about the aircraft, you get this 20K liquid H2 that you need to transport from a tank to the aircraft. If you think about a line in which you transport a 20K fluid, this line first must be cooled at 20K. Otherwise, you will have boiling everywhere. If you have boiling, you can imagine the pressure will go up. We know that because we use H2, liquid H2 for rocket engine. Ariane, for example, does that, and these guys are used to it. But the problem is that doing it in Kourou, that's where we launched our rockets, and doing it at Charles de Gaulle is not the same. Less people. The other problem, of course, is only to bring. We don't think we can bring, for example, for airport, you cannot bring the H2 to Heathrow or JFK. With trucks. You have to probably produce it on the place. So you can imagine the infrastructure to do that. And then, of course, we know that H2 leaks, and you have to wonder, what are you going to do with leaks? How do you handle leaks? So leaks, of course, you cannot do scenario of you cannot do experiments for all possible scenarios of leaks, okay? Leaks can happen anywhere. So this is why people would like to use a CFD to see that and to predict it. But then, of course, we go back to the problem I mentioned yesterday. Are we ready to do that? It's not clear. I want to mention two types of problems with H2. The first one is you have a leak and it does not ignite, but it accumulates. If it accumulates long enough, at some point it will ignite, but that's going to be an explosion. The other solution is that you have a leak, a hole somewhere, and right away there's a flame on it. And this flame is just sitting there. Well, sitting there, we will see in a second, it's sitting there, but the question is, if you are around, you may have a problem. So you've already seen that. The question today is what will happen with H2, and we already mentioned these simulations. Just remind you that in the same building, everything else being equal, the strengths of an H2 explosion is much more than it is for CH4, okay? You go by a factor of too large, let's say. So, so if you have explosions of H2, it will be much stronger than explosions of classical gases. So detonation, you know. So just to remind you that if you go to detonation, you just saw it, the overpressures will be enormous. So at Airbus, for example, the instructions are, we cannot have a detonation. We do what's needed to never have a detonation. It's not acceptable. Then the question is, how do you do, from a point of view of a combustion scientist, to make sure that you will never have a detonation? Well, that's a tough question. And as you remember, talking about deflagration to detonation, I mean, if you work for the Army, you want it to happen fast. We will want it to never happen. And that's obviously an unsolved problem. I think I've shown you already this, this video here, which looks like the video of Elaine, okay, of the transition of deflagration to detonation. And the point is, even when you talk, again, this is why it's important to have engineers in the loop, because of course, the big shots, you know, at Airbus, they say, detonation is a problem, let's cancel detonation. Okay, death is a problem, let's cancel death. You know, it doesn't work that way. I mean, detonation, in many cases, like this one here, you know, in a tube like this with obstacles, you know, making sure that this never happens is almost impossible. I mean, it's really tough. You have to, at the moment, I'm not sure it can be done. Now, the other way to do it, but that doesn't work, is to say, if there is a detonation, can we cancel it, the detonation itself? Can we kill it? One way to cancel detonations would be to put obstacles. And I will go to obstacles a bit later today. For example, here you have a range of cylinders and you see a detonation passing by, and basically the detonation doesn't care. Huh? Boom, it goes through. And we did the simulation and it's the same. Detonation doesn't care. That means you will need much smaller holes to be able to stop a detonation. Another simulation, another solution is some kind of sprinklers. And Total in France is working on that. So you have here an example of explosion in a building without powder. And in the next one, you're going to see they added the powder here. The powder is a sprinkler. It dissipates powder everywhere so that when the flame propagates, it propagates more slowly and it cannot go to detonation. So that works more or less. If you look at the overpressure, it's much less. It's true. But in practice, we don't really understand all the details here. And for the moment, these things are not installed anywhere. But it could be a solution. You know, if you detect H2, boom, you inject powder right away. The problem is that the powder goes away. If H2 comes from a leak, it comes back. And so the next time, you don't have any powder left. So again, if you talk about safety engineers, they make you crazy about this. Now, the other thing I want to mention here is that the explosions are not the only problem. Suppose that you have a problem with this 20K tank, that it has a problem of isolation. Then it will heat up. And if the liquid H2 starts to heat up, it will boil, and the pressure will go up. If the pressure goes up too much, those tanks are not done to go to high pressure. You will have to vent the H2 somewhere. So if you vent it, the H2 will come out of the plane. Here, for example, if the plane is flying, you will have an H2 plume behind it. Okay? Now, this H2 plume can do two things. It can stay where it is, or it can ignite. Now, imagine the pilot calling, saying, I have a small problem with, I have a flame behind me. Then that's a bad problem. This is where design also is interesting. So we work now with aircraft company to design the place to vent the H2 so that the flame will not ignite, or even if it ignites, it will be lifted and go away, you know, not stick to the aircraft. Because we don't like, you know, when flames stick to an aircraft, you know, the consequences. No? It's not a good idea. And they know that at Airbus. You know, this is a presentation of the technical director of Airbus. And you see this lens here. This is where they plan to eject the H2. But they don't really know how to do it, okay? They are not combustion guys. So they just say, oh, we're going to push it out as far away as we can, okay? But that's a good situation where you know where you're going to vent. But if now you have an accident or something which breaks, you can have a leak of H2, not necessarily here, you could have it anywhere, okay? So you could have, even in the engine, you could have suddenly, something leaking inside the engine. So now if it is inside the engine, imagine you have a leak of H2 ignited, and you have all the walls around it, you have the tube, you have the casing, it's not a good idea. So now again, the safety scenarios become a little bit complicated. This is also true for trains. We work with train company. They have the tanks on top here, but if it starts leaking and it ignites, it's a problem. Actually, by the way, the trains have this interesting characteristic compared to planes, is that they go in tunnels. Now, if they stop in the tunnel and they leak H2, this is exactly the scenario for explosions and detonation. So that they will not have to go and get the train. The train will come to them in multiple pieces. So I'm meeting them actually in 2 weeks. Those guys, they say, but we will never have a leak. Okay, yeah, sure, no way. And so you could also have leaks on airports or in railway stations, and you have to master all that. So there's a whole field here of science to do, and it's a field which is actually at the intersection between what we do and what the safety, the fire safety people do. And so that's quite an exciting domain. And again, maybe we'll go back to these mitigation systems, but in terms of combustion science, it's certainly a huge problem. Now, I want to talk also about these flames. The interesting thing about the leak is that it's a very generic problem for us. It's a jet in crossflow. You have a hole, a jet of H2, and you have air here. What's happening? Well, those of you, I've seen at least a couple of you who are studying this jet in crossflow for engines, but for safety, it's the same problem. It's actually a very complicated problem that people have looked at for a while, but for slow flames. Let's say for methane, for example, in oil refinery systems, you get these torches which are burning methane or propane. Now you have a crosswind coming from the right side. You can see the shape of these flames. And this is a simulation of a flame. Now the wind is coming from the left. Many of these flames are actually premixed because the combustion is not fast enough to keep the flame here. So this is not a diffusion flame. It is lifted. And you see here the occurrence ratio. And it burns as a premixed flame behind the torch. But for H2, it's not going to be the same game. H2, I want to show you this movie. The tank, or let's say the leaks, the pressure in the tank will be high. So it will be a very high-speed jet, probably supersonic. And then the fire which is created by that is interesting. So let me show you this guy, if it works. So this is a test, by firemen. They just take a car. In the car, there is a tank of hydrogen. And you will see they will open a small hole. And you will see, well, look at the flame of hydrogen now. You see the type of flame which is created by hydrogen is really not like in a fire, It looks, it's very strong, very fast, because you are burning H2 at supersonic speeds. So when you go there, you'd better be sure that you have a way to extinguish it. Now, we didn't talk at all about that during this course, but there's a very good paper by a guy called Kalgaji here that you can find easily if you just type his name on the web, who studied flames for oil companies. And you can show actually that if you are blowing a fossil fuel here and you're blowing too fast, you can quench the flame. But if you are blowing H2, you can never quench the H2 flame. Once a flame of H2 is ignited, you can blow here as fast as you want, you will never quench. You can even blow it from the side, and it's almost the same. It's very difficult to quench it. One question of Airbus is, if you're flying 600 kilometers per hour, can you quench it? And we don't know for the moment, but I think it's a valid question. So we know that H2 flames will burn for all speeds here, even when you go supersonic, and maybe you'll be able to quench them when you also go very fast for the air, so that you can lift this flame and make it go away. Now you can say, well, if you're careful, you don't ignite it. Okay? If I have a leak somewhere, and if I'm careful, I will not ignite this flame, I will only have a plume. Okay? Except that H2 is able to auto-ignite. That's a typical example. If you take a tube where you have H2 and air, and you break suddenly a diaphragm in between the two, because you have a boundary layer interaction near the walls, that's enough to heat up the hydrogen, and then when it meets the air, which is here, it auto-ignites. In other words, it is quite likely, well, let's say at least from a safety point of view, you have to consider it. It is quite possible that if you have here a jet of H2, the heating along the wall might be enough to make it auto-ignite. You won't even need to spark it, which is even worse. Which really means that if you have a leak of H2, it will ignite. In many cases. Actually, it happened already. We have lost, for example, places to refill cars in Norway. One of them just burnt away, I think, 3 or 4 years ago because of that, because once you have a leak of H2, it will probably auto-ignite anyway. So, of course, everyone plans to use CFD to study these scenarios. And as I said, remember that there are constants in all the models that we've been using for turbulent combustion. These constants have been tuned in the last 20 years for kerosene, for methane. But when we go to H2, things are so different, the regimes are so different. For example, you might move from premixed to diffusion flames. Now you have to redo everything. And that's going to be a tough question. I just want to conclude here by reminding you that going to H2 is not such a good idea for us because H2 is thinner in terms of resolution. That's the problem. It's faster. When you go to high pressure or to large domains, it will make our life difficult. And you've seen the presentations of Moshe. It also does funny things in terms of instabilities that we never see normally. So those things. Okay. This front should be flat, and it's not. So why is that so? Well, it's because, let me jump this. This will come back to that later. It's because of the famous Lewis number. Remember that? Moshe talked about it. When the Lewis number is small, and that's the case for H2, you can have thermodiffusive instabilities. Thermodiffusive instabilities, you can do them easily if you do DNS. You start from a plane of flame, you shake it a little bit, but you don't put any turbulence. You come back after a few milliseconds, and you will have this cells which appear everywhere, and there's no turbulence interaction to do that. You don't need it. Just to give you another visualization of that, this is a comparison here between a flame with Lewis equal unity ignited here, and the same here, symmetry, with a real Lewis number, with Lewis number equal 0.3. And you see, by the way, the difference between the two is that the one at the bottom makes cells and propagates like 3-4 times faster than this one. So you cannot, when you go to H2, be blind to thermodiffusive effects and say, oh, it's a detail. No, especially for explosions, it makes a huge difference. You cannot just hope that you can use the classical models. And all the teams, actually, for the moment, worldwide, are working on this problem. So, and of course, the question, this is all laminar. But now, what if there is turbulence on top of it? Moshe talked about that this morning for small levels of turbulence. I just want to show you another simulation, which is probably a bit more precise than his. Doing something where we did a test where we compared 3 flames. A methane air flame at stoichiometry, a hydrogen air flame at phi equal 0.45, and an ammonia hydrogen flame at phi equal 1, but a content of NH3 of this same level. How did you pick them up? They all have exactly the same flame speed. Okay. And they all have almost within 5% the same flame thickness. So if you're using a turbulent combustion model where the only input is flame speed and flame thickness, these 3 flames should be exactly the same. Okay? Because the turbulent combustion models, you've seen them yesterday, they are blind to the details. Actually, you've seen also the correlations of Moshe. They use only flame speed and flame thickness. So we did a Lamina Flame first with these 3 cases, and that's, again, a Bunsen flame. So the flames are stabilized here. You have the burn gases, the fresh, and here you see alpha, and we talked about that already. Sin alpha is SL over U. It's a flat premixed flame, and all of them are exactly the same length within a few % here because they are tuned to do that. Okay? They have the same flame speed. So we checked that for a laminar flow, they were exactly the same. And now we're going to send turbulence into them from this place here. So this is a rather big DNS, okay, with complex chemistry. And you have the three results here. The CH4 on top, ammonia in the middle, and H2 at the bottom. So you see it from the start, and you see that they look same at the beginning, but when they go to steady state, the CH4 and the ammonia flames are kind of long, and the H2 flame is much, much shorter. So even so, they had exactly the same laminar characteristics. As soon as you put them into turbulence, they react in a different way. These results have been confirmed by other groups in other configurations. And the overall result, when you look at the mean flame, is that the H2 flame is like 2 times shorter than the two other flames. And of course, those have Lewis numbers close to 1. This one has a Lewis number close to 0.3. So that means that if your turbulent combustion model now doesn't have some way of knowing that, it's desperate. I mean, a factor of 2 is too big. So why does it burn 2 times faster? Well, actually, you can look at the isocontours here of reaction rate for CH4 in a cut, here for H2. You recognize the thermodiffusive instabilities, you know, burning less here and more here. But when you really look for the baseline cause of this shorter flame, you can prove that it's linked actually to I0. I0 is the mean consumption speed, Moshe talked about that this morning too, along the flame front, and SL0 is the unstretched laminar flame speed. And you see that for methane, for example, this is close to unity, but for hydrogen, it's burning 2 times more. And that's a mystery that has been puzzling us, and also the group in Aachen, and many people have the same experience, is that this H2 flame, as soon as it is curved, each element here is burning 2 times faster than the laminar flame speed. I'm not saying it is more wrinkled, right? The wrinkling is the same. It's just that the laminar flame speed increases by 2. Heinz-Pitch has found cases where it increases by 4 or 5. Remember when we discussed that yesterday, I said most flames have an I0 of 1. That was true for classical fuels. For hydrogen, obviously, there is something happening that we don't understand. Actually, people are fighting about the exact explanation. Is this due to strain or to curvature? Or it's quite a question at the moment. So to conclude on H2, it's clear that you're going to see more and more of it, maybe not on aircraft, but certainly for many other applications, that the safety will open a brand new field for combustion experts. That will be a very important issue. And for the first time, people will rely more and more on CFD. So it's better than nothing, okay? Don't believe it's the truth. But clearly, CFD here will have to work fast to get up to date on H2 flames because they combine all these things that we never had before. Detonation, thermodiffusive instabilities, very fast flame, faster than mixing. All of that has to be accounted now in codes, and it's going to take some work. Okay, I will stop here on H2. Maybe you can take a few minutes for questions before we move to Flammal Interaction. Yes?
One of the issues is the benefit and that destination wave, the destination wave just because of the different decline.
It's, yeah.
So, if we were to think in terms of safety, would it help if we just have emissions downstream when we can somehow detect the detonation wave instead of what happens in RDT is not required.
Yeah, I agree. It's a possibility. But again, as soon as you talk to safety people, they ask you all kinds of questions like, what about the people around? And you don't know where the leak will be. You don't know where the mixture will be. So you want a system which works all the time. And that makes it much more difficult to imagine. Yes?
Hydrogen flames are much less radiative.
Yeah.
That's a problem for like solution to that?
Well, if you want radiation, or if, for Alison actually has shown me pictures like this. People want to replace fires with wood with fires with hydrogen. Then you need to find a way to make the hydrogen flame radiate. Otherwise, you don't even see them. Okay, it's not useful. So you can add. It's easy to add things to make them radiate. Yeah, because otherwise you don't see them. Huh? That's a problem actually for firemen, because you can have a H2 flame which you don't see. So now they have to get equipped with infrared systems so that they don't get cut in two when they pass in front of a flame. You know. So radiation for H2 flame, same thing. It hasn't been much studied for the moment. People didn't care, but it has to come. Yeah, I agree. Yes. Okay. The question is, what about NOx? Whatever you do now today, as soon as you talk about, I have an H2 burner, people will tell you, you control NOx. It is not easy, but for the cases I've shown you, we keep NOx under what's regulated. We can do it. But it is obviously very dangerous. If you start having diffusion flames, then you don't pass for NOx. And so NOx is going to be one of the main problems. It's also a problem with ammonia, of course. It's a problem with actually, it's surprising that NOx is so constraining for these methodologies, but clearly it is. NOx will be a big problem. But the good news for CFD is that we have the NOx schemes. We already do computations of H2 flame with NOx, so CFD should help to see how to control the NOx formation. So that's not too bad, but it may be a showstopper. That's the reason why they stopped H2 in piston engines. BMW had an engine like this 15 years ago. They could not make the NOx go down enough. So it is clearly a big question. Another one, before we go to the last talk on flammal interaction, and then you can go home. Oh, sorry, I didn't see it. I was watching up there.
So what do you think would be like a good way for, especially with these hydrogen flames, because we always want to operate lean for the most part, with respect to like thermodiffusive instabilities becoming so wrinkled that they generate problems with possible like turbulence. Like, what do you think would be?
Yeah, that's a very interesting question. We know that in a gas turbine, we need to go extra lean. You know, they're talking about 0.2 with hydrogen. And then if you go 0.2, you're going to have thermodiffusive instabilities. Then you have people like Heinz Pitch in Aachen who says, well, I don't know, thermodiffusive instabilities are not a problem, they are a functionality. They can help us making shorter chambers now. So there is this possibility that you use thermodiffusive instability to help you, to make your flame shorter. But then you have to rethink, you have to build an engine in which the thermodiffusive instability is an added capacity. And for the moment, they don't exist. Okay, it's just, we don't know, because you must be sure that they will always be there. Okay, otherwise the engine will not operate. But yeah, we have to be extra lean. Yes?
I have another question about kinetics. The carbon wood paper. Initial delay gets really off in already like 7. But why is it so difficult to make them?
Oh, it's not, well, yeah, the question is, why is it difficult to build a good H2 scheme, you mean, for low temperature chemistry?
Yeah, like to
yeah, I think it's not. I think it's just that the kinetics experts have not looked into it too much, but I'm sure this will be done easily for H2. We get quite good schemes already, okay? The H2 is really the fuel for which we have the best schemes for the moment. So I'm not too worried about that. The fact that it doesn't work for detonation is a specific issue, but for deflagration, I'm sure it will work well. And most CFD guys can do it. Yes?
Are there researches that looks into HHO gas?
Well, yeah, sure, but I wouldn't be able to give you names like this. Yeah, sure, it's another possibility. Yeah. Again, I've shown you that H2 is one entry gas, then you can have all the other gases behind them. Okay, so I propose to finish with a a fun talk. Well, it's not so much fun, but about flammal interaction. That's the one topic we did not touch, and I think it's important that you get an idea about that. Flammal interaction is what you expect it to be. Okay, it's a flame touching a wall. Why is it important? Remember that all flames have high temperatures, higher than the temperature that any metal can sustain. So obviously there is an issue here. You don't want to explode your chamber right away. So why do we care actually? We care because flames obviously influence walls, but walls also influence flames because they cool them, just because we cool the walls so the walls can survive. When we cool the walls, at the wall, the temperature goes down, and so the reactions go down. So there are some species which don't burn. So when you cool a wall too much, you produce pollutants, and that's, of course, that's not good. Note also that walls influence acoustics, and we talked about combustion instabilities. If you put your head into a fighter aircraft in the post-combustion chamber, you look at the holes, they are multi-perforated everywhere. And without these holes, they are there for cooling, they are also there for stability. If you remove them, the engine gets unstable right away and it explodes. So the holes and the walls play a big role also in the fields of acoustics. And because the acoustics will control the instabilities, which also control the flame. So there are many people in gas turbine company, actually in all companies, working on walls and on cooling. That's a very important problem. Okay, so we're going to talk mainly about the walls which are in the chamber here because those are the hottest parts of the engine. When you talk to an engineer, again, the guy will tell you that he doesn't expect you to help him for efficiency. Efficiency of a gas turbine does not depend on the chamber. That's surprising to say, but it depends on the compressor. Everything you inject in a good chamber burns 99% of the fuel. You cannot burn more. Okay? The only way to increase efficiency is to increase the pressure. And that's where the chamber plays a role, because if you increase the pressure, you increase the temperature, and then the walls start burning. Because, of course, not burning is the first condition, actually, in an engine. And, of course, once you have done 1 and 3, well, you can also limit the pollutant emissions. But if you cannot satisfy 1 and 3, you are in trouble. And then if you are in trouble, walls will just go away, okay? That's an example of a few problems in an aircraft. So if you look at the swirler here, remember that we have the swirler, the chamber, and these walls here, and then you have the walls of the turbine. That's the first stage of the turbine here, what you call it the high-pressure stator. This guy receives the combustion products right away. Imagine you are sitting at the end of the chamber and it comes right into your head. So you have to be able to survive. And for us CFD people, it means you have to be able to predict the thermal load on these things. Now, if you do a simulation like this one, you see here these pockets of burn gases hitting the walls. And here, there is no combustion anymore. But in the chamber, there is combustion going on, okay? So you can still have here a flame touching a wall, and that's the worst case, of course, because that's the place where you get the highest heat flux. So I just want to mention also here that we're going to talk about, well, the turbine and the walls of the chamber. There are cases like rocket engine where there, on purpose, you do strange things with the walls, you let them burn. Okay, normally you shouldn't do that, huh? But there's no other way in a rocket engine because the fluxes are so high. So normally, everything we do here is done to avoid combustion on the walls. The walls themselves must survive. As I said, in a rocket engine like this one, you have these carbon-carbon rockets here with nozzles. These things will burn, and then you will have very complicated things. You will have combustion in the gas, and the walls themselves start burning. I'm not touching that for the moment. There are people working on that. It's not for us. So what's happening in a chamber? In a chamber, if you let the flame like this and you do nothing at the walls, they will just die. So you not only cool them by this side, you actually multi-perforate them so that you create a film of cold gases here, or cold They come from the compressor, so they are at 700 K. It's cold compared to the 2000 K here. So this film here of air protects the wall from the hot products. And so if you look at a real chamber, this is how it looks. This is an helicopter chamber. Each of these holes here is there to inject a little bit of air. You go through a volcano cloud, for example, in which you have some solid particles. These solid particles melt in the compressor. When they arrive in the chamber, they still melt, and then they enter here, they freeze on the holes, and they block them. Once you have blocked 10 of them, then you get a hole in the chamber. That was one of the reasons why aircraft companies did not want to fly, you know, when you had volcano doing stupid things a few years ago. So this is a simulation of the flow in a hole. This hole is 0.5 millimeter, okay? It's very small. And you see here the film which is created, and this film is the only thing between you and the ground. Huh? If you lose that, the hot gases which are here will touch the wall, and the wall will die. This is actually a much bigger simulation here, where you have a whole set of holes, and you see the turbulent structure. You should not have too much mixing, okay? You want to keep some cold gases here near the wall to protect you. Because if you would put directly the gases on the walls, it would be tough. That's a full chamber simulation where you see the films created everywhere here. And you try to keep this flame under control, okay? You don't want it to touch the walls. Now, it happens from time to time, but normally it should be quite limited. After a while, these things get colder, and normally you can allow them to come closer to the wall of the chamber. Now, it's the same when you go to the stator. Again, the stator here will receive burn gases coming from the chamber, and you may have to cool it. This time you cool it from the inside, and you evacuate some gases. And again, here, the CFD part of this thing is quite interesting. And as I said, you cannot block these holes, okay? If you plug one of the holes, then you start having difficulties. So, for the moment, I'm going to just tell you why we use holes by not using holes. That means I'm going to take a smooth wall and send the flame on it. That's called Flammal Interaction. There are many configurations when you have a wall and a flame. The first thing is that if the wall is far away from the flame and is only feeling fresh gases, there's no problem. Then the wall also can be in the burn gases. And then you have a problem of heat transfer. And the worst situation is that the wall is at a place where a flame comes from time to time and hits the wall. That's the highest flux there, and that's the situation we want to avoid. So, in other words, if you put here a sensor on this wall, you will have moments where the flux is low because you are in the fresh gases. You will have moments where the flux is high because you are in the burn gases. And there you have moments where the flux is very high because you are under a flame front. Now, can we predict these things? Well, actually, you can do quite a few things. This is the baseline situation here on top, which is called head-on quenching. So you take a 1D flame, and you send a flame to the wall. The wall is cold. The flame arrives on the wall. So the flame will quench. But at the same time, the flux through the wall will be large. And the question is, what happens? You can do also sidewall quenching. That's the case where the flame propagates along a wall, like in a tube. And the question is, what is the heat flux between the wall and the flame front? And this is a movie of flammal interaction when we also compute the temperature in the wall. The first thing I want you to note is that the range of temperature is not the same in the wall. This is a metal wall. A metal wall which receives one flame is not enough to go to high temperature. Okay? It will heat up by 10 K or something. Of course, if you repeat the experiment, it will be more, but one flame is not enough to heat up a lot this wall. You have here the temperature. Here you have the fuel mass fraction, and here you have the reaction rate. So if you look at the reaction rate, the flame will move here and then suddenly die. That's the moment of flame quenching. Okay, now, and then the flame is finished. Okay? If we track an ISO contour of temperature, for example, if we track this point, it will go to the wall, stop here, and then go back because of diffusion. Look at this point here, up, and then it's going back because now everything is quenched, and we only have heat diffusion in the gas. This is for propane air at 1 bar. And so if you plot versus time, the flame speed, the consumption flame speed, I'm not talking about displacement at all here, you see that when the flame is far away, now this is the wall distance here between flame and wall, the flame comes to the wall. For the moment, it doesn't sense anything, it keeps going. Then suddenly it hits the wall, it quenches, and you see the wall distance stops here, and then the flame recedes after that. So you can compute the heat flux through the wall, and this heat flux will be enormous. It's easy. If you don't believe me, just put your finger on the flame, you will see that it's a high flux. So we're interested in two things: the distance at which the flame can come closer to the wall, and the flux, which will be found in the wall. When you measure the fluxes, you can do that, you know, it's just in your metal, you add some sensors for temperature, and you can back up the flux. You see those fluxes here are in megawatt per square meter. Okay, this is enormous, okay? So you are of the order of 0.5 to 1, depending on the flame, and the fluxes go up usually when the wall is at a higher temperature, then the flux is even higher, which is not a good idea, again, for safety. That's also why H2 flames are a problem, because if they come closer to walls, the walls will have a very high heat flux, and they will become wet, and they might actually melt. So one very nice thing about Flammal Interaction is that we have, again, theoretical results, which we can easily match with simulations and experiments. And they tell you the following thing. They tell you that if you compute the flame power, which is just rho Cp delta T multiplied by SL. Okay, this is the amount of flux that the flame can generate. And you normalize the maximum wall heat flux by that, you find almost always the same thing, except for hydrogen, you find about 0.3 something. In other words, if you want to remember a simple rule, when the flame touches a wall, it will deliver 1/3 of its power as heat flux to the wall, and then it will die. Okay? That's simple enough. Now, the other thing which is interesting is to wonder about the distance at which the flame will stop from the wall. You see here the flame comes to the wall, then it stops, and then it goes away. We can normalize that by the famous delta. Now you know what delta is, okay? It's D over SL, and it's always the same order of magnitude, about 3. That means the flame comes to the wall and it stops at a distance which is 3 times. All the fuel which remains here is not burned. The flame doesn't go there, so it will go out as a pollutant afterwards, for example, in a piston engine. So during head-on quenching, the flame will stop at approximately 3 times the flame thickness, and then it will die, quench. So as I said, these unburned hydrocarbons which are left are a problem, because you cannot finish them, okay? They are in a zone which is too cold, close to the wall. When you do sidewall interaction, it's exactly the same thing, except that instead of 0.3 for the flux, you have 0.15, and that means the distance here between the wall and the flame extremity here is 7 times the delta, which is D over SL0. Now, this is for laminar cases. If you do turbulent cases, then, well, the flame will come close to the wall and quench locally as a head-on quenching, and then it will move laterally as a sidewall quenching. All these things will happen one after the other, and you have to combine them. Now, I want to talk about one thing which is probably, surprisingly, one of the most important things for our society in the last 200 years, and it's tube quenching. Now, if you take a tube and you put 2 walls, and the flame which must propagate between these 2 walls, imagine the flame is losing temperature here and losing temperature here. If it loses too much, at some point it will stop and it will die, okay? This is called tube quenching. Typically, the tube quenching radius diameter here, 2R, is like 50 times delta. Delta, you remember, it's like a few tenth microns, so 50 times that is like 0.5, 1 millimeter or something like this. So if the hole here, if the tube is less than 0.5 millimeter, you cannot have a flame go through it. So you might say, hey, why is it telling us that this is important? This is actually very important. because it proves that in the tube, if the tube is big, then the flame will propagate, and it propagates almost at the laminar flame speed. If the tube is smaller, it propagates at a lower speed, and if the tube is very short, less than 50, it does not propagate at all. You have flame quenching. So this was measured. That's also a very famous book. Actually, you should have one. The Lewis and von Elber is old, but it's pretty good. And you have tube diameter for quenching here as a function of occurrence ratio. So when the flame is very energetic, very close to stoichiometry, the tube cannot be too big because the flame thickness is small. And when you have a lean flame or a rich flame, you can have a larger tube. So you see 0.3 centimeters here. If you have a tube smaller than that, you cannot have a flame there. So I want to talk about two applications of that, which are quite important. The first one is flashback protection. In many premixed systems, you face this problem. You have premixed gases here, and you have seen 2 days ago that you can have a flame trying to go there. If you put here a grid with holes which are small enough, well, you will prevent that, okay? That's called the flame arrestor. You can actually buy those things. This is one here.
Back over the lip
here you have the movie. You see that if we would have had this system installed here, we would have stopped the flame.
In this case, transition is caused by...
The detail there is that those things are built to survive flashback. When I did my PhD, we did not use that. We used only a grid with holes. And after 1 year, when we opened it, there was a big hole in the middle because it will stop the flame once, okay? But then maybe it will melt after that. So we were operating. We thought we had the flame arrestor, but we didn't have one. Lucky. Now, second application, that's where history comes into the picture. The reason why we have global change today is because we started burning stuff. The first thing we burned after wood was coal. Where do we get coal? In the mine, okay? In the mine, there is a small problem. When you dig coal out, you also have CH4 and other gases. Those gases burn really well. They even explode. It's a recipe for explosions is to put CH4 in a mine and to wait until it ignites somewhere. So you might say, let's not bring anything which can ignite it. Okay, but in those days, there was no electricity, so you needed light. So how can you go in a mine with a lamp, because you need a lamp, which uses combustion, and not explode everything? Well, that's the idea of this guy, Davy. Davy was a lord, you know, so any English guys in the room? Okay, I'm going to be careful. Davy was a lord, he was also a scientist, and he actually took a patent. When you see it, 200 years ago, the guy was smart. He took a patent and he wrote a paper which is quite famous. And he said, let's do the following thing. Let's take a flame with a grid around it, and the grid will take it small enough so that the holes are smaller than 50 times the flame thickness. He did not have all these details, but he knew that there was a dimension here which was such that the flame would not come out. So instead, inside the lamp of Davy, you would have a light, a flame. The light would come out, but not the flame. Okay? So that's great. You can go down in the mine. Even if there is CH4 outside, the flame cannot go through. Okay? And the second lesson of that is that at the same time, there was another guy who was not a lord, Stephenson. It's quite interesting because Stephenson published exactly the same results as Davy. I think a few months before something. It's actually an example where that people use quite often. You will find it on the web. And Davy accused Stephenson that, that Stephenson copied his results, which was absolutely not the case. It's like always like this. So if you have an idea, you can be sure that someone else has the same idea at the same time because it's the right time for this idea. But the problem is that Stephenson was not a lord. So he lost, okay? And so the main people that people know about it today is Davy. He got also extremely rich because, of course, everyone bought Davy lamps for mines, okay? Now, this is not the end of this fascinating story, and I will conclude on that by giving you an example of, and it's not a joke, people don't believe it, but it's true, of the way people were handling CH4 leaks in mines a few centuries ago. So imagine you have a mine here, so it's coal everywhere, plus gas. This gas is usually CH4, so it's lighter than air. So usually if you have a leak here, of course, you know it's the fault of the workers. Okay, who else? So usually if people detect CH4, we stop operating, and of course the boss stops paying you. And then everyone was on the ground on top and saying, okay, how do we fix this problem? Well, today we have pumps when we can pump out the CH4. In those days, one solution was to burn it. How do you do that? Well, you have to burn it. Of course, you can burn it by just igniting it brutally, in which case you will have a big explosion. That's not the very good solution, okay? And if you make the list, you hear a lot of people talking about the dangers of nuclear energy, but if you look at coal, I mean, this is killing much more people every month. Look at the numbers here. Only China, this is the worst accident. On average, it's thousands of people getting killed by that. So it's a big problem. So you want to avoid that, and still you want to operate your mine. So you have to find a way of evacuating CH4. So I'm not, this you have seen already. So we won't want the bad way of burning this thing, so let's look at the good way. What's the good way? The good way is the following. If you wait long enough, CH4 being lighter than air will go up. Okay? And all the CH4 will be stuck here near the ceiling. Now, if you look at that with your combustion eyes, you say, oh, this looks like a diffusion configuration. I have air at the bottom and fuel at the top. So if I can ignite here a small flame, I will actually see a diffusion flame on top here, which will burn everything. Then the question is, how do you ignite it? Okay, you take the youngest guy. It's not a joke. Read the papers, you will see. You take the youngest guy, you don't tell him exactly what's going on, and you give him a Davy lamp, okay, so that he can see where he goes, because otherwise he won't see. And the guy goes, usually he crawls in the mine. He crawls because there is much more air at the bottom than at the top. So if you crawl, you have only air. And then he goes where there is fuel, he removes the grid, and he raises his hand, okay? So now you have two solutions. You know, this is where you learn about premixed versus diffusion. Either you really have a segregation here, there was no movement, so nothing was mixed, and you really had the fuel on top, and then you create a very nice double, triple flame here. That's a lot. Huh? One going left, one going right. Actually, you see that sometimes in Hollywood movies, you know, it will make a big blue sheet on top, which will actually swallow some of the air and some of the fuel. If you do that for a few minutes, it's very slow flames, then you will clean up all the CH4. And then you can start operating the mine again. The second solution, of course, that it was not diffusion, it was premixed. So if there is a premixed zone here, it's the same result, but with a premixed flame, in which case you kill the young guy, but you can start operating also. So in both cases, you're good, okay? And again, I tell you, it's not a joke. Go read the papers. But that's not the worst part, wait. The worst part is that once you have an explosion in a mine like this one, you have usually a fire. This fire can burn forever. We don't know how to stop it. It's like a barbecue of 2 kilometers square, you know? And so it keeps burning forever. The example here of this city in Pennsylvania, it started burning in '62. It's still burning, okay? We don't know. They tried everything to stop burning. They cannot do it. So, you know, the solution, if you have a fire, is to quench it right away. That means if you have an explosion, you send water. That, they know how to do that, you know? You pour water into the mine so that you can start operating again after 2 weeks or 2 months, you know. And the most famous example, well, Prussia is here that killed 22,000 people, but the most famous example is this Radbod story. In Radbod, they had an explosion at 4:20 in the morning. They don't know exactly. They think maybe it was one of the guys who opened his lamp or something, or maybe it was not completely, you know, safe. And they had 400 people. Only a few escaped. And at 7 in the evening, the boss decided to flood the mine completely. So the families were on top here. The guys were below. And they said, okay, probably they're all dead. And they sent the water. Okay, so I think it's better to do a PhD in combustion. Huh? Okay, I'm going to stop here. I think you've got enough. Maybe we can just take a few questions before we adjourn. Any comment or question? Anyone wants to work in a mine? Okay, it was a long week. I'd like to thank you. It was very, very good for me to interact with you. I hope you have a good career in combustion. Keep burning. I think there's lots of things to do. And I hope you have a safe trip home. Thank you.